So then when sort of taking this k-nearest neighbor and going back to the images, you can see that it's actually not very good. Here I've colored in red and green which images would actually be classified correctly or incorrectly according to their nearest neighbor. And you can see that it's really not very good. But maybe if we used a larger value of k, then this would involve actually voting among maybe the top 3 or the top 5, or maybe even the whole row. And you could imagine that that would end up being a lot more robust to some of this noise that we see when retrieving neighbors in this way. So another choice we have when we're working with the k-nearest neighbor algorithm is determining exactly how we should be comparing our different points. For the example so far, we've just shown this, we've talked about this L1 distance, which takes the sum of the absolute values between the pixels. But another common choice is the L2 or Euclidean distance, where you take the sum of the square root of the sum of the squares, and take this as your distance. Choosing different distance metrics actually is a pretty interesting topic, because different distance metrics make different assumptions about the underlying geometry or topology that you expect in the space. So this L1 distance, underneath this is actually a circle according to the L1 distance, and it forms this square shape thing around the origin, where each of the points on this is on the square is equidistant from the origin according to L1. Whereas with the L2 or Euclidean distance, then this circle is a familiar circle. It looks like what you'd expect. So one interesting thing to point out between these two metrics in particular is that the L1 distance depends on your choice of coordinate system. So if you were to rotate the coordinate frame, that would actually change the L1 distance between the points. Whereas changing the coordinate frame in the L2 distance doesn't matter. It's the same thing no matter what your coordinate frame is. So if your input features, if the individual entries in your vector have some important meaning for your task, then maybe somehow L1 might be a more natural fit. But if it's just a generic vector in some space and you don't know which of the different elements, you don't know what they actually mean, then maybe L2 is slightly more natural. And another point here is that we can actually, by using different distance metrics, we can actually generalize the k-nearest neighbor classifier to many, many different types of data, not just vectors, not just images. So for example, imagine you wanted to classify pieces of text. Then the only thing you need to do to use k-nearest neighbors is to specify some distance function that can measure distances between maybe 2 paragraphs or 2 sentences or something like that. So simply by specifying different distance metrics, we can actually apply this algorithm very generally to basically any type of data. So it's actually even though it's a kind of simple algorithm, in general, it's a very good thing to try first when you're looking at a new problem. So then it's also kind of interesting to think about what is actually happening geometrically if we choose different distance metrics. So here we see the same set of points on the left using the L1 or Manhattan distance, and then on the right using the familiar L2 or Euclidean distance. And you can see that the shapes of these decision boundaries actually change quite a bit between the two metrics. So when you're looking at L1, these decision boundaries tend to follow the coordinate axes. And this is, again, because the L1 actually depends on our choice of coordinate system, where the L2 sort of doesn't really care about the coordinate axis. It just puts the boundaries where they sort of should fall naturally. So actually, my confession is that each of these examples that I've shown you is actually from this interactive web demo that I built, where you can go and play with this k-nearest neighbor classifier on your own. And this is really hard to work on a projector screen. So maybe we'll do that on your own time. So let's just go back to here. Man, this is kind of embarrassing. Okay, that was way more trouble than it was worth. So let's skip this, but I encourage you to go play with this in your browser. It's actually pretty fun and kind of nice to build intuition about how the decision boundary changes as you change the k, and change your change your distance metric and all those sorts of things. Okay, so then the question is, once you're actually trying to use this algorithm in practice, there are several choices you need to make. We talked about choosing different values of k. We talked about choosing different distance metrics. And the question becomes, how do you actually make these choices for your problem and for your data? So these choices of things like k and the distance metric, we call hyperparameters, because they are not necessarily learned from the training data. Instead, these are choices about your algorithm that you make ahead of time, and there's no way to learn them directly from the data. So the question is, how do you set these things in practice? And they turn out to be very problem dependent. And the simple thing that most people do is simply try different values of hyperparameters for your data and for your problem and figure out which one works best. There's a question? So the question is where L1 distance might be preferable to using L2 distance. I think it's mainly problem dependent. It's sort of difficult to say in which cases you think one might be better than the other. But I think that because L1 has this sort of coordinate dependency, depending on the coordinate, it actually depends on the coordinate system of your data. If you sort of know that you have a vector and maybe the individual elements of the vector have meaning, like maybe you're classifying employees for some reason, and then the different elements of that vector correspond to different features or aspects of an employee, like their salary or the number of years they've been working at the company or something like that. So I think when your individual elements actually have some meaning is where I think maybe using L1 might make a little bit more sense. But in general, again, this is a hyperparameter, and it really depends on your problem and your data. So the best answer is just to try them both and see what works better. So then the question, I mean, even this idea of trying out different values of hyperparameters and seeing what works best, there are many different choices here. What exactly does it mean to try hyperparameters and see what works best? Well, the first idea you might think of is simply choosing the hyperparameters that give you the best accuracy or best performance on your training data. This is actually a really terrible idea. Like, you should never do this. And in the concrete case of the nearest neighbor classifier, for example, if we set k equals 1, we will always classify the training data perfectly. So if we use this strategy, we'll always pick k equals 1. But as we saw from the examples earlier, in practice, it seems that setting k equals to larger values might cause us to misclassify some of the training data, but in fact lead to better performance on points that were not in the training data. And ultimately, in machine learning, we don't care about fitting the training data. We really care about how our classifier or how our method will perform on unseen data after training. So this is a terrible idea. Don't do this. So another idea that you might think of is maybe we'll take our full data set and we'll split it into some training data and some test data. And now I'll try training my algorithm with different choices of hyperparameters on the training data, and then I'll go and apply that trained classifier on the test data, and now I will pick the set of hyperparameters that cause me to perform best on the test data. This seems like maybe a more reasonable strategy, but in fact, this is also a terrible idea, and you should never do this. Because, again, the point of machine learning systems is that we want to know how our algorithm will perform. So the point of the test set is to give us some estimate of how our method will do on unseen data that's sort of coming out from the wild. And if we use this strategy of training many different algorithms with different hyperparameters, and then selecting the one which does the best on the test data, then it's possible that we may have just picked the right set of hyperparameters that caused our algorithm to work quite well on this testing set, but now our performance on this test set will no longer be representative of our performance on new unseen data. So again, you should not do this. This is a bad idea. You'll get in trouble if you do this. What is much more common is to actually split your data into 3 different sets. You'll partition most of your data into a training set, and then you'll create a validation set and a test set. And now what we typically do is go and train our algorithm with many different choices of hyperparameters on the training set, evaluate on the validation set, and now pick the set of hyperparameters which performs best on the validation set. And now, after you've done all your development, after you've done all your debugging, after you've done everything, then you take that best performing classifier on the validation set and run it once on the test set. And now that's the number that goes into your paper. That's the number that goes into your report. That's the number that actually is telling you how your algorithm is doing on unseen data. And this is actually really, really important that you keep a very strict separation between the validation data and the test data. So for example, when we're working on research papers, we typically only touch the test set at the very last minute. So when I'm writing papers, I tend to only touch the test set for my problem in maybe the week before the deadline or so to really ensure that we're not being dishonest here and we're not reporting a number which is unfair. So this is actually super, super important, and you want to make sure to keep your test data quite under control. So another strategy for setting hyperparameters is called cross-validation. And this is used a little bit more commonly for small data sets, not used so much in deep learning. So here the idea is that we're going to take our test data, or we're going to take our data set, as usual, hold out some test set to use at the very end. And now for the rest of the data, rather than splitting it into a single training and validation partition, instead we can split our training data into many different folds. And now in this way, we kind of cycle through choosing which fold is going to be the validation set. So now in this example, we're using 5-fold cross-validation. So you would train your algorithm with one set of hyperparameters on the first 4 folds, evaluate the performance on fold 4, and now go and retrain your algorithm on folds 1, 2, 3, and 5, evaluate on fold 4, and sort of cycle through all the different folds. And when you do it this way, you get much higher confidence about which hyperparameters are going to perform more robustly. So this is kind of the gold standard to use, but in practice, in deep learning, when we're training large models and training is very computationally expensive, this doesn't get used too much in practice. Question? Yeah. So the question is a little bit more concretely, what's the difference between the training and the validation set? So if you think about the k-nearest neighbor classifier, then the training set is this set of images with labels where we memorize the labels. And now to classify an image, we're going to take the image and compare it to each element in the training data, and then transfer the label from the nearest training point. So now what we're going to do with the validations, so now our algorithm will memorize everything in the training set, and now we'll take each element of the validation set and compare it to each element in the training data, and then use this to determine what is the accuracy of our classifier when it's applied on the validation set. So this is kind of the distinction between training and validation, where your algorithm is able to see the labels of the training set, but for the validation set, your algorithm doesn't have direct access to the labels. We only use the labels of the validation set to check how well our algorithm is doing. A question? The question is whether the test set, is it possible that the test set might not be representative of data out there in the wild? And this definitely can be a problem in practice. The underlying statistical assumption here is that your data are all independently and identically distributed, so that all of your data points should be sort of drawn from the same underlying probability distribution. Of course, in practice, this might not always be the case, and you definitely can run into cases where the test set might not actually be might not be super representative of what you see in the wild. So this is kind of a problem that dataset creators and dataset curators need to think about. But when I'm creating datasets, for example, one thing I do is I'll go and collect a whole bunch of data all at once, using the exact same methodology for collecting the data. And then afterwards, you go and partition it randomly between train and test. One thing that can screw you up here is maybe if you're collecting data over time, and you make the earlier data that you collect first be the training data, and the later data that you collect be the test data, then you actually might run into this kind of shift that could cause problems. But as long as this partition is random among your entire set of data points, then that's how we sort of try to alleviate this problem in practice. So then once you've gone through this cross-validation procedure, then you end up with graphs that look something like this. So here on the x-axis, we are showing the value of k for a k-nearest neighbor classifier on some problem. And now on the y-axis, we are showing what is the accuracy of our classifier on some data set for different values of k. And you can see that in this case, we've done 5-fold cross-validation over the data. So for each value of k, we have 5 different examples of how well this algorithm is doing. And actually, sort of going back to the question about having some test sets that are better or worse for your algorithm, this is sort of, using k-fold cross-validation is maybe one way to help quantify that a little bit. And in that, we can kind of see the variance of how this algorithm performs on different of the validation folds. And that gives you some sense of not just what is the best, but also what is the distribution of that performance. So whenever you're training machine learning models, you end up making plots like this, where that show you what is your accuracy or your performance as a function of your hyperparameters. And then you want to go and pick the model or the set of hyperparameters at the end of the day that performs the best on the validation set. So here we see that maybe about k equals 7 probably works about best for this problem. So one thing that is, so k-nearest neighbor classifiers on images are actually almost never used in practice because they're just with all of these problems that we've talked about. So one problem is that it's very slow at test time, which is kind of the reverse of what we want, which we talked about earlier. Another problem is that these things like Euclidean distance or L1 distance are really not a very good way to measure distances between images. These sort of vectorial distance functions do not correspond very well to perceptual similarity between images, how you perceive differences between images. So in this example, we've constructed, there's this image on the left of a girl, and then 3 different distorted images on the right, where we've blocked out her mouth, we've actually shifted down by a couple pixels, or tinted the entire image blue. And actually, if you compute the Euclidean distance between the original and the boxed, the original and the shuffled, and the original and the tinted, they all have the same L2 distance, which is maybe not so good because it sort of gives you the sense that the L2 distance is really not doing a very good job at capturing these perceptual differences between images. Another sort of problem with the k-nearest neighbor classifier has to do with something we call the curse of dimensionality. So if you recall back this viewpoint we had of the k-nearest neighbor classifier, it's sort of dropping paint around each of the training data points and using that to sort of partition the space. So that means that if we expect the k-nearest neighbor classifier to work well, we kind of need our training examples to cover the space quite densely. Otherwise, our nearest neighbors could actually be quite far away and might not actually be very similar to our testing points. So and the problem is that actually densely covering the space means that we need a number of training examples, which is exponential in the dimension of the problem. So this is very bad. Exponential growth is always bad, and you're never going to get enough. Basically, you're never going to get enough images to densely cover this space of pixels in this high-dimensional space. So that's maybe another thing to keep in mind when you're thinking about using k-nearest neighbor. So kind of the summary is that we're using k-nearest neighbor to introduce this idea of image classification. We have a training set of images and labels, and then we use that to predict these labels on the test set. Question? Oh, sorry. The question is what was going on with this picture? What are the green and blue dots? So here, this was maybe we have some training samples which are represented by points, and the color of the dot maybe represents the category of the point of this training sample. So if we're in 1 dimension, then you maybe only need 4 training samples to kind of densely cover the space. But if we move to 2 dimensions, then we now need 4 times 4 is 16 training examples to densely cover this space. And if we move to 3, 4, 5, many more dimensions, the number of training examples that we need to densely cover the space grows exponentially with the dimension. So this is kind of giving you this sense that maybe in 2 dimensions, we might have this kind of funny curved shape, or you might have sort of arbitrary manifolds of labels in different dimensional spaces. And the only way that because the k-nearest neighbor algorithm doesn't really make any assumptions about these underlying manifolds, the only way it can perform properly is if it has quite a dense sample of training points to work with. So this is kind of the overview of k-nearest neighbors, and you'll get a chance to actually implement this and try it out on images in the first assignment. So if there's any last-minute questions about KNN, I'm going to move on to the next topic. Question? Sorry, say that again? Yeah, so the question is, why do these images have the same L2 distance? And the answer is that I carefully constructed them to have the same L2 distance. But it's just giving you this sense that the L2 distance is not a very good measure of similarity between images. And these images are actually all different from each other in quite disparate ways. But if you're using KNN, then the only thing you have to measure distance between images is this single distance metric. And this kind of gives you an example where that distance metric is actually not capturing the full description of distance or difference between images. But yes, in this case, I just sort of carefully constructed these translations and these offsets to match exactly. Question? So the question is, maybe this is actually good because all of these things are actually having the same distance to the image. That's maybe true for this example, but I think you could also construct examples where maybe we have two original images, and then by putting the boxes in the right places or tinting them, we could cause it to be nearer to pretty much anything that you want, right? Because in this example, we can kind of like do arbitrary shifting and tinting to kind of change these distances nearly arbitrarily without changing the perceptual nature of these images. So I think that this could actually screw you up if you have many different original images. Question? The question is whether or not it's common in real-world cases to go back and retrain on the entire data set once you've found those best hyperparameters. So people do sometimes do this in practice, but it's somewhat a matter of taste. If you're like really rushing for that deadline and you really got to get this model out the door, then if it takes a long time to retrain the model on the whole data set, then maybe you won't do it. But if you have a little bit more time to spare and a little bit more compute to spare, and you want to squeeze out maybe that extra 1% of performance, then that is a trick you can use. So moving on so we kind of saw that k-nearest neighbor has a lot of the nice properties of machine learning algorithms, but in practice, it's not so great and really not used very much in images.